In this unit, we will study electrochemistry, which is the study of reactions that involve electrochemical changes, and therefore they are systems that involve electricity. We're looking at spontaneous reactions that actually produce electricity, or non-spontaneous reactions that need electricity in order to occur. The basic reactions that are occurring here are called oxidation-reduction reactions. And there are lots of common examples such as the rusting of iron, the action of bleach on stains, and photosynthesis that are oxidation-reduction reactions and involve the transfer of electrons from one species to another. The first examples of reactions that were studied of this type among scientists involved oxygen. The combustion of fuels and the reaction of metals with oxygen to give oxides were described as oxidation. So something like iron reacting with oxygen to form rust was called oxidation because it was the addition of oxygen that was causing the reaction. Removing oxygen from metal oxides to give their metals was described as reduction. So for example, if a metal ore was extracted from the ground and the pure metal was extracted from that, the metal ore was said to have been reduced to its elemental form. So this is where the terms oxidation and reduction come in. Further studies showed that there are actually many more reactions that involve this more general phenomenon, which is where electrons are being transferred from one substance to another. So for example, in the iron example, when iron reacts with oxygen to form rust, as you know from looking at this, we're forming an ionic compound. The iron here is changing from having no charge to having a positive charge. And so in the process of oxidation, the iron has actually lost electrons. The reverse process, or removing the oxygen from the ore or from the rust, would involve reduction or a gain of electrons. So when we speak generally about oxidation-reduction reactions, oxidation is the process of losing electrons, while reduction is the process of gaining electrons. There's a mnemonic device that you can use to help you remember this, and that is Leo the lion says grr. Loss of electrons is oxidation, gain of electrons is reduction. Now we have studied oxidation reactions at several points during our study of chemistry. So for example, when we look at single displacement reactions or lots of synthesis reactions, like the formation of an ionic compound, these often involve a loss and gain of electrons or a transfer of electrons. Now, one of the things when we're studying oxidation-reduction reactions that you're going to find that we do is that we split the reactions into what are called the half reactions. So we look at the oxidation and the reduction reactions separately from one another. So if we look at the case of sodium chloride being formed, so the reaction of sodium plus chlorine to form sodium chloride, we can look at the two half reactions that are occurring here. So in this case, the sodium is reacting to form sodium ions. So the sodium is forming sodium ions. In the process, it has lost an electron. So an electron is a product in this particular half reaction. In the case of chlorine, the chlorine is gaining electrons to form chlorine ions. So its reduction half reaction shows that it's gaining electrons, or the electrons are essentially a reactant in this process. So this reaction is the oxidation half reaction, and this reaction is the reduction half reaction. Now we can also refer to substances as either being the oxidizing agent or the reducing agent. The oxidizing agent is the substance that is allowing something to be oxidized. So it's allowing something to lose electrons. So therefore, it is the substance that is reduced. By gaining electrons, an oxidizing agent allows a substance to be oxidized. So in this case, the chlorine is the oxidizing agent. The reducing agent is the opposite. It's the one that donates the electrons, and in this case, it is the sodium. Okay, this is another example here of a burning strip of magnesium. The magnesium atoms are losing electrons to become cations, and the oxygen molecules are gaining electrons in the formation of the oxide. Now, the way that we track electrons in a chemical reaction in order to identify which substances are being oxidized or reduced is using what are called oxidation numbers. Oxidation numbers are used to keep track of the electrons during the chemical reaction. Now, in ionic compounds, the oxidation numbers are the same as the charge of the ions. So, for example, in sodium chloride, we know in this ionic compound, sodium has a +1 charge and chlorine has a -1 charge. And these are also their oxidation numbers. So the oxidation of sodium is +1, the oxidation of chlorine is -1 in this case. Now, it's less clear for molecular compounds, because if you have a molecular compound, so something like H2O, we know that these substances have not been formed by a transfer of electrons. So within a molecule of H2O, hydrogen and oxygen do not have a charge. So therefore, in order to keep track of electrons, we're not looking at charges, we're looking only at oxidation numbers. You can think of oxidation numbers as being the charge that the atoms would have if the substance were ionic. So if the electrons were transferred completely from one atom to the other in the formation of these compounds, these would be their charges. Now, in order to determine the oxidation numbers in the elements of a compound, what we need to do is use a set of rules. And we're going to follow these rules in order. Okay? And there are going to be some things that are different that you wouldn't necessarily expect. So we'll go through some examples so that you can see the different scenarios. Now, in your notes on page 2, there's a pretty extensive list, very detailed with exceptions and more descriptive set of rules for assigning oxidation numbers. Okay, I've got the simple version of those rules listed here, and we're going to apply these rules to a number of examples. Now, in terms of the exceptions, what you're going to find is that if you follow the rules in order, you're very unlikely going to need to memorize any exceptions per se. All right, so first of all, the basic rule is that elements have an oxidation number of 0, which makes sense because there is no charge and there is no presumed ionic compound that would come out of that. So anytime you have an element, its oxidation number is 0. Now let's look at some examples here. We've got CO, so carbon monoxide. When we look through the rules, the first rule that applies is that oxygen has an oxidation number of -2. Okay? And this is as expected. For oxygen, it's always -2, and that's what you would expect in an ionic compound. If you thought about oxygen with its 6 valence electrons and gaining 2 electrons, it makes sense. Now, for the carbon, okay, what you'll find if you look at the chart on page 3, you can see that carbon actually has more than one possible oxidation state. Okay, much like something like iron can be +2 or +3, carbon also has more than one oxidation state. So there's not a rule that we're going to use specific to carbon. What we're going to do is use the sum rule. So when you have oxidation states, they sum to the charge on the particular molecule or the ion. So in this case, carbon monoxide has no overall charge. So what that means is that the carbon must have an oxidation number of +2, okay, in carbon monoxide. Okay, if we look at carbon dioxide, okay, oxygen is -2. Okay. In order for the sum of the oxidation states in carbon dioxide to sum to 0, the carbon in this case needs to be +4, okay, because there's 2 oxygens, so that gives a total of -2. So the carbon must be +4 in order to have a 0 sum. With sodium hydride, sodium is an alkali metal, and alkali metals, as the rules suggest, will always, as expected, have a +1 oxidation state. Okay, so in this case, hydrogen must be -1 in order for the sum to be 0. Now this, if you read through the detailed rules, you'll see that hydrogen is often +1, but there is an exception when it's in a metal hydride. And as you can see by following the rules in order, we didn't need to know the exception off the top of our head. It naturally was determined by following the rules. All right, with this magnesium titanium oxide, okay, the rules tell us magnesium is +2 and oxygen is -2. Now, just to be clear, what we're doing is showing the individual oxidation states of the elements. So each magnesium in this has an oxidation of +2. So to figure out what titanium is, what we need to do is look at the fact that we've got 2 at +2, plus we've got titanium, plus we've got 4 oxygens, each at -2, and that all needs to equal 0. When we solve this, we can see that titanium must have an oxidation state in this particular compound of +4. With this copper dichromate, the only element that is given is oxygen. So there are different techniques for helping us when we've basically got 2 unknowns. When we've got an ionic compound, so this is an ionic compound, we can actually break it up into its ions and we can simplify the process. So this breaks up into copper plus and Cr2O7 2-. Okay, so we can see the copper here has a +1. By breaking it up into its ions, we see that's the charge and the oxidation state of copper. Okay, then we can either solve using the whole molecule or we can solve using just this ion here. Oxygen is -2, so 2 chromines plus -14, which is 2 times the oxygen, has got to equal -2, because in this case the sum of the oxidation states needs to equal the sum of the charge. Okay. And when we solve this, we find that each chromium is therefore +6. Okay. Both chromiums together is +12, so each individual chromium is +6. Okay. In this case, you've got an alkali earth metal of magnesium with +2, and the nitrogen is -3. In this particular one, it's a straightforward ionic compound, so the charges on each of the elements are as predicted, their oxidation states. KClO3, potassium is +1, the oxygen is -2, and using the zero-sum rule, we get +5. Okay, in this particular one, the only one that's given is oxygen, so if I split it up into its ions, I can see that the chromium's oxidation state is +3. Oxygen is -2, and nitrogen in this case is +5. I have done a lot of examples for this to try to show you the process. Okay? Being able to find the oxidation numbers will be useful to identify which substances are gaining and losing electrons in a chemical reaction, which you'll see momentarily. Okay, this chart, which you see in the bottom of page 3 of your notes, shows the various oxidation states of lots of elements. When you're in grade 10, you focus on copper, lead, and iron, and you learn that they have more than one possible charge. Okay, as you examine further, something like chlorine, which you may have thought, because it's what you're used to, that it's going to just be -1 all the time, as with the other halogens. Okay, in actual fact, it's only fluorine that has one possible oxidation state. Okay? Chlorine and bromine and iodine can form many, many different compounds and therefore have many different oxidation states. Okay? The metals, the transition metals that have more than one oxidation state are quite interesting because the different oxidation states actually give different colors of the substances. Okay, so let's put this to use. We want to use oxidation numbers in order to decide what's happening in a particular chemical reaction. We're going to identify what's been oxidized, reduced, and what the oxidizing and reducing agents are by monitoring the oxidation states. So what we'll do is we'll start by identifying what the oxidation states are of the elements in the chemical reaction. So in this case, the elements hydrogen and chlorine have 0. Then in the products, we've got +1 and -1. Okay, so as we can see here, the hydrogen has gone from 0 to +1, while the chlorine has gone from 0 to -1. So the hydrogen in this case has lost an electron, and the chlorine in this case has gained an electron. Okay, when something becomes more negative, it's caused by the gain of electrons. So with this information, we can identify the substance oxidized, okay, to be hydrogen. So the substance that has lost electrons has been oxidized. The substance that's been reduced is the chlorine. It's the one that has gained electrons. The oxidizing agent, okay, is the substance that has been reduced. It is the substance that is helping the oxidation to occur. So whatever is reduced is the oxidizing agent, and whatever is oxidized is the reducing agent, which in this case is the hydrogen. So when you're identifying the substances oxidized, reduced, and the agents, it's always going to be reactants that you are giving. Okay, now this is a more complicated reaction, but it doesn't mean we can't identify what's been oxidized and reduced. What we need to do is go through systematically and determine every single oxidation state of each element in every single compound. Okay, so chlorine is +1, potassium is +1, chlorine is -1. So you're systematically going through, doing the steps that you did on the previous example. I'm going to put some down below here. So you have to go through and determine the oxidation numbers of every single element in the reaction. Now, not every single element is going to have a change in oxidation state. Only the substances that are being oxidized and reduced will experience a change. So what we need to do is look for an element that has changed. So for example, manganese. Okay, this should be +4 here. Okay, manganese has changed from +4 to +2. And the chlorine has changed from -1 to 0. Okay, so in this case, the chlorine has lost electrons and the manganese has gained electrons. The other elements like potassium, oxygen, sulfur have not changed their oxidation number, so they're not involved in the oxidation reduction. So we can now identify the substance oxidized, which is also the reducing agent, and the substance reduced, which is also the oxidizing agent. So the substance that has been oxidized here is KCl, specifically chlorine within KCl, but the entire substance is the KCl. And the substance that was reduced or gained electrons was the MnO2. Okay, so that is one skill that's important in oxidation reactions, to be able to identify what's been oxidized and reduced. The next major skill in electrochemistry is balancing redox reactions. And because these reactions involve the transfer of electrons, the balancing of equations is a little bit more involved. And it's often also because when we're studying redox reactions, we're going to be using reactions without the spectator ions. So that makes it a little bit different for balancing the equations. At first glance here, this reaction of Fe3 plus Sn2 plus goes to Fe2 plus Sn4 plus. At first glance, it looks balanced. Okay? The atoms on both sides of the reaction are balanced, and that's our main concern with balancing reactions. But there's another thing to concern ourselves with, and that is balancing the charge. If you look at this reaction, on the left-hand side, the overall charge is +5, while on the right-hand side, the overall charge is +6. And what that means is that this reaction, although at first glance it looks balanced, it's actually not balanced. So what we need to do is balance the reaction by ensuring that the electrons that have been transferred in this reaction are in fact balanced. So this example is going to be used to show you the basic principles of balancing the electrons in an equation. I know that some of you would be able to study this a little bit and use your math skills in order to determine what the coefficients would need to be to give rise to a balanced equation, both with atoms and charges. Okay, but I'm going to show you the half reaction method for balancing reactions. So the first step is to divide the reactions into the two half reactions. So in this case, the iron 3 plus is changing to iron 2 plus, and the tin 2 plus is changing to tin 4 plus. So these are the two half reactions. Now these are unbalanced. Okay? The atoms are balanced, but we need to make sure that the charges of the half reactions are balanced, and we do that by adding electrons to the appropriate side. So in this first reaction, okay, the left side has a +3 charge and the right side has a +2 charge. So if we add 1 electron to the left-hand side of this reaction, it will now be balanced both in charge and atoms. In the second reaction, we need to add 2 electrons to the right-hand side in order to balance it. Now we can see why the original equation wasn't balanced in charge, as the first half reaction involves gaining 1 electron, while the second half reaction involves the loss of 2 electrons. And what we need to do is balance the transfer of the electrons. So the least common multiple of this is 2. So what we're going to do is we're going to multiply this first reaction by 2. Okay, the second reaction, we don't need to do anything. Okay, so this is the actual half reaction that's happening. Need to multiply everything by 2. Okay, and then our final step is to recombine the reactions, and we're going to add the half reactions like we've done in the past, okay, and simplify the electrons. Okay, now as you're used to, there's no electrons visible in a chemical reaction. Okay, so you expect and you want, when you recombine the half reactions, for the electrons to cancel one another out. And we're given the overall balanced reaction of Sn2 plus the iron 3 plus goes to 2 iron 2 plus the tin 4 plus. So if we re-examine this reaction, the atoms are balanced, okay? In this case, the charge is also balanced. The charge on both sides is +8. Okay, so much like in grade 10 when you would systematically go through and balance the atoms and check the left-hand side and the right-hand side, we can do the same in redox reactions, checking the atoms. The additional step is to check the charge. Now this was a simple reaction that didn't have any oxygen involved and didn't have an acid or a basic system. It was a basic single displacement type reaction, okay, where you've got two metals reacting with each other, and it's an activity series reaction. When you've got reactions involving hydrogen and oxygen, we need to know the conditions of the reaction. So it's either going to be acidic or basic, or it could possibly be neutral. And these steps are going to be a little bit more involved for balancing. We're going to use water and hydrogen ions in order to balance the atoms. Okay, so let's look at this particular reaction, manganese, permanganate reacting with hydrogen sulfite to produce sulfate and manganese ions. Now we're going to do a demo in class to model these reactions. And what you're going to find from the demonstration is that permanganate actually behaves differently depending on the conditions. So whether it's acid or base, it's going to react differently. Now the goal of balancing this reaction is the same. We want the atoms to be balanced, and we also want the charge to be balanced. So the steps are the same overall. Essentially what we're doing is we're going to break the reaction up into half reactions, balance the individual half reactions, ensuring that the electrons are balanced, and then recombine them. So in this case, the half reactions, we've got the permanganate converting to Mn2+, and you've got the hydrogen sulfate reacting to form SO4 2-. Now, the very first step of balancing the half reactions is to ensure that the atoms other than hydrogen and oxygen are balanced. So in this case, the manganese, I've got one manganese on either side, so I'm good there. The sulfur, I've got one sulfur on either side, so I'm good. The next step is to balance the oxygens by adding water to this reaction. So in this case, I'm going to add 4 waters to the right-hand side. And in this case, I'm going to add one water molecule to the left-hand side. The next thing that I'm going to do is balance the hydrogens by adding H+. Okay, so I'm balancing an acid here. Okay, in the first reaction, I need to add 4H+ to balance the acids. Actually, sorry, 8H+. I've got 8 hydrogens on that side. And on the second reaction, I need to add 4H+. Now, with more molecules and ions involved, determining the charges and balancing the charges of the half reactions is something that you need to be very careful of. Okay, so in this particular reaction, on the left-hand side, I have a total of +7, okay, and on the right-hand side, I have a total of +2. So what that means is I need to, in order to balance this, I need to put 5 electrons on the left-hand side in order to make the charge on both sides +2. In the second reaction, I've got no charge here, and I've got +2 here. So in order to balance this one, I need 2 electrons to be added to the right-hand side. Now, as you're going, you'll be able to kind of monitor and check your work, because if you've got these 2 half reactions, one of them should be oxidation and one of them should be reduction. In this case, this first reaction is showing the gain of electrons, and the second reaction is showing the loss of electrons. So you shouldn't have the electrons on one side of the equation. Okay? You'll know that something has gone wrong in your balancing, if that is the case. Now, as you can see from the oxidation reduction here, the 5 electrons that's being gained is not the same as the 2 electrons that's being lost, so we need to balance those. And so to do that, I need to multiply the first reaction by 2, and I need to multiply the second reaction by 5, because the lowest common multiple here is 10. Okay, and I'm going to write this out, being very careful to multiply every single ion and molecule by the factor that I've decided. Okay, so these are the 2 balanced half reactions, and now I'm ready to recombine them. So I've got the electrons will simplify, okay, the H2O will simplify, I'll have 3 on this side, the H+, I'll have 4 on this side. So my overall reaction here is 2MnO4 minus, okay. And when you look through here, the manganese, you've got 2 on either side. The sulfur, you've got 5 on either side. The hydrogen, you've got 10 on either side. The oxygen, you've got 23 on either side. Okay, and the charge is -2 on either side. Okay, so all of the atoms, okay, and the charge are balanced. Oftentimes when students first are learning the steps here, they're a little bit puzzled as to why, starting from the skeleton reaction, we need to do so many steps in order to come up with the balanced chemical equation. Okay? A few little things here. When we know that the conditions are acid or base, that doesn't necessarily mean that we know which side the hydrogen or the water will potentially be on, or whether or not there are going to be any H+ or H2O molecules in the overall balanced equation. And the challenging part is to balance the electrons. So it would be difficult from this to know that the coefficients in front of the manganese were going to need to be 2, and in front of the sulfur compounds were going to need to be 5 without examining the half reactions. Okay, so hopefully you can appreciate that in the end, when you get good at this and when you're fast at it, this is a much easier approach to balancing equations than trying to determine what the coefficients will be otherwise. Now, sometimes redox reactions occur in basic solutions, so we need to be able to also balance in basic solution. When we are balancing in acid, we would use the H plus and the H2O to help us to balance the hydrogen and oxygen atoms. In basic solution, the ion we have is hydroxide, and we still have water that we can use to balance the hydrogens and oxygens. Now, I hope you can appreciate that although we could do it, it would be much more difficult to determine how many hydroxides and water molecules needed to be on either side of a particular half reaction to balance the oxygens and hydrogens using OH minus and H2O than using the H plus and the H2O. Using the H plus and the H2O, I can use the water to balance the oxygen, I can use the hydrogen to balance the hydrogen, and they don't affect one another. So what we're going to end up doing when we balance in base is actually following the same steps as we did before. We're going to balance completely in acid, and then we're going to use a little bit of chemistry to help us switch it to balancing in base. So for this particular reaction, what I'd encourage you to do is even pause the video right now and balance this in acid. So follow the same steps as you did before. Okay, so divide into the two half reactions, balance the two half reactions using the H plus and the H2O, balance the electrons. Okay, when you balance this in acid, what you are left with is 2H plus 3 SO3 2 minus plus 2 MnO4 minus 3 SO4 2 minus plus 2 MnO2 plus H2O. Oops. Okay. So if you balance this in acid, following the same steps as we did for the previous example, this would be the reaction. Now what we're going to do is we're going to convert this to being in base by using a little bit of chemistry. This has two H pluses on this side, and what we want to do is switch this from being an acid to base. So we're going to do that by getting rid of this H plus. I can get rid of this H plus by adding 2 OH minus, because as you know, H plus and OH minus is actually equal to water. Now if I add 2 OH minus to this reaction on the left-hand side, I'm going to throw it out of balance. But if I just do the same thing to the opposite side, so if I add 2 OH minus to the right-hand side as well, I really have not done anything in terms of balancing this reaction. The charge is still balanced, the atoms are still balanced, okay, when I add OH minus to both sides. Okay. Then what I'm going to do is combine these here. This really is equal to 2H2O. Okay, so I'm going to combine them, and I've also got H2O on this side. So if I've got 2H2O on the left and 1H2O on the right, what that actually means is that what's left over is 1H2O on the left-hand side. Okay, so overall, in base, Okay, this is the balanced equation. You can see that now I've got hydroxide present, so it's in base. Okay, the H2O is on the other side, but it really doesn't matter what side the H2O is on or the OH minus is on. If we look through the balancing, we've got 3 sulfurs on either side, 2 manganese on either side, 2 hydrogens on either side, 18 oxygens on either side, and the charge on either side is -8. Okay, so the atoms and the charge are balanced in this reaction, and it's balanced in base. Now, the redox reactions that you can encounter in the reaction question in the AP exam can sometimes be a little bit complicated. And so there's a few tips that I've got here that will help you to determine what the reactants and the products are going to be. There are some common oxidation reduction conversions that you need to know. So you've seen the first two in the previous two examples. You saw that permanganate in acid tends to go to Mn2+, and permanganate in base tends to go to MnO2. Okay, there's some other common ones here that I've tried to present to you. There's going to be a few things. So one of the things that you can do is try to remove the spectators first when you know that you've got a redox reaction. And there's a few things to look out for. The best thing for us to do is to go through a couple of examples. Now, what we're not going to balance these. What we're going to do is write the skeleton reactions for these. So with the 2 reactants and 2 products, what you would actually be expected to do is to balance them once you've determined what the changes are going to be. So let's look at a couple examples here. So a solution of potassium dichromate is added to an acidified solution of iron 2 chloride. So in this case, we've got dichromate. So we want to recognize that dichromate is something that's commonly reduced. Okay, and it's in an acidified solution, which is important to us. So from this, we can see automatically that one of the things that's changing is the Cr2O7 2- is actually being converted to the chromium ion, or Cr3+, because it's in an acid solution. We also know that when we're balancing, we're going to be balancing this in acid. The second piece here is to figure out what is being oxidized. So we've got a solution of iron 2 chloride. So we've got Fe2+, and we've got Cl-. And the Fe2+ can be converted into Fe3+, so it can actually lose electrons. And the chlorine, if it lost electrons, would be converted into Cl2. Now we'll delve a little bit further into this later, but if you look at the activity series or the reduction potentials, you would see that this is actually a more likely oxidation in this case. So what we're dealing with is Fe2+ converted into Fe3+. So once you've used the word equation to come up with the skeleton, then you need to go through the 8-step process to balance that reaction. So you need to split it into the 2F reactions and go through the whole process to balance the charges and the atoms. All right, with this next one, we've got a concentrated solution of hydrochloric acid. Okay, so we know that we've got acid, but we also know that we've got HCl, so chlorine might be involved. And we've got powdered manganese dioxide. So powdered manganese dioxide is MnO2. Okay, in an acid solution, that is converted into Mn2+. Okay, so we know that that has been reduced, okay, because in manganese, is +4 in the MnO2 and it's gone to +2. So we know that it's been reduced. So we need something else that's going to be oxidized. The only other atoms we have are hydrogen ions and chlorine ions, and hydrogen is already oxidized, so our only option here is for the chlorine ions to be oxidized to Cl2. Okay, and there's your skeleton equation, and then you would balance that in acid. Okay, this next one here, potassium permanganate solution is added to an acidic solution of hydrogen peroxide. So you've got H2O2. Permanganate is the MnO4 minus. Okay, it's a solution, so I'm taking out the spectator right away to make it easier. Okay, and hydrogen peroxide, okay, when it is oxidized, will often change to O2 and H2O. Okay. So really, when you're setting up your half reactions here, you can do H2O to O2 and the permanganate to the Mn2+, and then you can balance this in acid. And this is the reaction that you did with the titration. And next one here, a stream of chlorine gas, okay, is passed through cold solution of sodium hydroxide. Okay, so you've got sodium hydroxide, you know that you've got a base. Okay, chlorine in this case, okay, is being reacted. Okay, and at first glance, this doesn't look too clear what's going to happen. So you suspect, okay, I've got sodium ions. Could they gain electrons? That's kind of unlikely. Okay, the sodium hydroxide is going to set up conditions for base, and there's also some oxygen present there. This is one that is rare, but you want to keep your eye out for, where it's really difficult to see what might happen. And what occurs in this case is something that's called disproportionation. And disproportionation is when you've got one substance that's both being oxidized and reduced. Okay, so chlorine in this case, when it's just chlorine, has a 0 charge, and if it becomes an ion, Cl minus, then in that case it's gaining electrons. But if it combines with oxygen to make something like ClO minus, okay, then, or hypochlorite, then it has lost electrons. So in this case, it's really hard to see, okay, but if you get really stuck, you want to try to think of how disproportionation might have occurred. And then when you're doing the half reactions for here, you've got chlorine going to Cl minus and chlorine going to ClO minus. Okay. This next one, I chose this example because we're starting with solid sodium dichromate. Okay, it's still acidified. Okay, so we still have the Cr 2O7 2 minus in acid, so we know it's being converted to Cr3 plus, and we know that that's a reduction, so we're looking for something else that's been oxidized. Okay, so we've got sodium ions and we've got chlorine ions. And sodium has already lost electrons, so our option here is for iodine to lose electrons to become iodine solid. Now in this case, what I would recommend that you do is balance, okay, without the spectator ion involved. Okay, pretend there's no spectator, or there's a spectator of sodium, but then you need to be clear that in the final reaction you need solid sodium dichromate, and then the sodium is going to be an ion in the end. Okay, so really what you're working with here is solid sodium dichromate reacting with iodine to produce the chromium ion on the iodine, and then you're going to have sodium as an ion. Okay, so once you've figured out what the balancing is by using the half reaction method, okay, then you can reintroduce the the sodium, and you just need to balance the sodium afterwards. Okay, so I'd recommend, and you are going to be doing an assignment on this, but I would recommend that you go through and practice these. And these are examples from your original note in reaction chemistry, and there are many more examples that you can examine there. Okay, so we are really now just looking at stoichiometry in redox reactions and titrimity in redox reactions. The basics of the balancing and all that kind of stuff has already been done, and now what we're going to be doing is applying it and using stoichiometry. So when you're doing stoichiometry with redox reactions, it is pretty much the same in terms of the ratio and stuff like that. What you do need to be mindful of is the spectator ions. So I always find it easier to balance the reactions without the spectators, so remove them. And then when you're doing the stoichiometry, you just want to be mindful of the spectators because the molar masses that you use will need the spectators. So in this reaction here, we've got sodium sulfite and potassium dichromate in acidic solution. So the spectators are sodium and potassium. You've got sulfite, and sulfite converts to SO4 2-, and the dichromate, as we've seen a couple of times, converts to chromium ions. So you need to balance this in acid, so I'd encourage you to pause the video and balance so that you can practice that skill. One big thing about this one that you haven't seen in any examples yet so far is that the very first step of balancing the other atoms needs to be done. So chromium here, you need a 2 there. Okay, it's not going to work unless you are mindful of that. Okay, so when this is balanced in acid, the final reaction that you have is this here. Okay, once you've balanced it, you want to double check and make sure that the charge and the atoms are balanced, okay, which I've done and made sure. Okay, and now we can do the stoichiometry. So the question is, how many grams of sodium sulfate are needed to react with 12.4 grams of the potassium dichromate. So you're starting with 12.4 grams of potassium dichromate. Okay, so you need to be careful when you're finding the molar mass to include the spectator, but also be mindful of the charges of potassium and the dichromate. So it's K2 Cr2O7. So the number of moles here is 12.4 divided by 294.2. Okay, so the moles of the potassium dichromate is 0.042. Okay, then we need to apply the ratio, much like we would in regular stoichiometry problems. So there's 3 times the amount of sulfate is required. So the number of moles of the sulfite is 3 times that. Okay, which is 0.1264. Okay, and for every 1 mole of SO3 2-, we get 1 mole of sodium sulfite because the ratio is 1-to-1 in terms of the spectator or the sulfite ion. Okay, so that is also the moles of the Na2SO3. Okay, and that's something that you're constantly going to need to be mindful of in stoichiometry in redox problems. Okay, so then when I'm finding the final mass, I'm going to use the molar mass of the sodium sulfite, which is 126.05, and that gives me a total of 15.9 grams. Now you've seen redox titration. So in a redox titration, we're using the titrant is something that changes color. So in our case, the permanganate that we used changed color from purple to colorless as it was reacting with the hydrogen peroxide. And so once the hydrogen peroxide was all consumed, then a pale permanent pink was produced. Okay, so in redox titrations, the titrant can actually act as an indicator as well. So we're doing an example here where we've got a sample of iron ore, a 2-gram sample of iron ore, and we're dissolving it in acid. And so all of the iron in that sample is being converted into Fe2+. So now we've got this solution where we've got Fe2+, and we're going to titrate that solution of Fe2+ with permanganate. Okay, and it's in an acidified solution. So in acidified solution, the permanganate converts to Mn2+, and in this case, the iron, it tells us, will be oxidized to Fe3+. So using the information from the question, we've got our skeleton equation here, which can then be balanced using the half reaction method in acid. Okay, so this is the balanced equation. And so what we're given here is that we're starting with the 2-gram sample, and we're given that we titrate that sample with the 0.1 molar permanganate, and the volume of the permanganate that's required is 27.45 milliliters. So the moles of permanganate that's reacted with the iron is 0.002745. So that's step 1, is to find the moles. Okay, step 2, we use the ratio. So the moles of Fe2+ that we have is actually 5 times that. Okay, so 0.013725. And then we can find the mass of the iron from that. Okay, for every 1 mole of Fe2+, that came from 1 mole of Fe. So there's 1-to-1 ratio. So the moles of iron in the original sample are the same as the moles of the iron 2+ in the original sample. So that would give us a mass of iron of 0.7665. Okay, so as a percentage, we had a 2-gram sample, and that's the mass of the pure iron in that sample. And so as a percentage, it's 38.3%, which was found by taking the 0.7665 and dividing by 2 times 100. And that gives us the percentage. Now in C, it's saying, what if the iron was actually in the sample as Fe2O3? And if it was in the sample as Fe2O3, the ratio between the iron and the iron oxide and the Fe2+ would not actually be 1-to-1, okay? Because for every 1 mole of the iron oxide, we actually have 2 moles of the Fe2+. So what that means is when we are working backwards, we've got, in step 2 up here, we know the moles of the Fe2+ that we had, but the equivalent moles of iron oxide is actually half that amount. So the moles of iron oxide here is 0.006825. And so if we find the mass then, it's 1.0959, and the percent in the 2-gram sample is 54.8%. Okay, so the percent of pure iron in that sample is 38.3. The percent of Fe2O3 is 58.4. Okay, so that's how you do that distinction. So this concludes our lesson in the basics of redox reactions and the stoichiometry and balancing of the reactions.